All right, so this is Stokes Law, and this largely is used to talk about sedimentation rates. And the basic notion here, and you'll see when you do these problems, is that if you've got a bunch of different particle sizes, right, the large particles will actually move down faster than the small particles, which I guess we sort of know that, but this is a formula for this. So if this thing is moving at some velocity v through this thing and has some radius r, okay. And it's moving through a fluid that has a viscosity of, what is that, nu? Okay. Then, it's not nu, is it? I should know what that is. Is it a V? I don't even know. Okay. Then the force upward on this thing, the drag force on this thing, which I think that's what the thing is, right? Okay, is equal to 6 pi times the viscosity times the radius times the velocity that it's traveling. Okay. Which is interesting, right? Because you'd think, well, yeah, okay, good enough. All right, so because it's like, okay, wait, small radius might have a small force, but yeah, we'll get into why small radii actually go more slowly through the fluid. All right, so let's look at we'll look at an example. So a droplet of water mist has a radius of 4.8 microns. So that's, by the way, 4.8 times 10 to the minus 6 meters. What is its terminal velocity if it falls through air? And that's the viscosity of air, right? Ignore the buoyant force. Okay, so we're going to ignore the fact that there's going to be a buoyant force upward on the droplet as well as this, okay? We can do that with air because air has a density of about 1.29 kilograms per cubic meter, right? Compared to the water droplet has a density of 1,000, so it's really a small correction. If it's a chunk of rock falling through water, we really can't ignore the density of the water. So one of the example problems that you're going to work out here deals with that, deals with how do you do with buoyant force with that. Okay. Okay, so let's figure this out. What's its terminal velocity as it falls through air? So this thing is going to have a force of gravity acting down on it, right? And when the force of gravity equals this drag force, it's at terminal velocity. That is, the drag force equals its weight. And the reason it reaches terminal velocity is that the V keeps getting bigger and bigger and bigger. Everything else stays the same. When the V gets big enough, the drag force equals the gravity force, right? So let's figure out the force of gravity on this thing, right? So the force of gravity is just m times g. M is the density times the volume, and I'll make my volumes look like that so you won't confuse them with velocities, right? Times g, and then that is equal to the density of the water, right? 1,000 times 4/3 pi, the radius. Okay, let's see. Now that's its radius. Okay, so the radius is 4.8 e minus 6, and that's to the third. That's a 4, not a 9. All right, so this is my volume, and then times 9.81. So I'm going to figure out this is now the force of gravity. So it's not going to be big, right? 1,000 times 4 divided by 3 times pi times 4.8 e minus 6 raised to the third power. Then I have to hit the right arrow times 9.81. All right, here we go. Okay, so, oh, that's cool. It's a repeating. Is it repeating? It's a cool number. 4.5, and then it's 4 4s, and then a bunch of 9s. And it's 9, 9, 9, and then that's times 10 to the minus 12th newtons. Okay, so this is the force of gravity. Okay, if that equals the drag force, okay, then we can figure out the velocity that it's got, right? So the drag force is, we're going to go force of drag, right, is going to be 4.5444999 times 10 to the minus 12th newtons is equal to 6 times pi times the viscosity of air, right, 1.81 times 10 to the minus 5th, right, times, let's see, what are we, we're here, okay, radius, oh, there's a radius here and a radius there, here a radius, there a radius. Everywhere a radius, radius. We could have simplified this, is what I'm saying. like one of the radii would cancel out. Okay, so we got a radius there. And I guess we're solving for v, right? Is that right? So 6 pi viscosity, right? Radius velocity. Okay, so I'm going to take the number that's on my calculator, divide by 6, divide by pi, divide by 1.81 e minus 5, divide by the radius, 8 e minus 6, and I should get my velocity. And I get 2.7749 times 10 to the minus third meters per second. All right, 1 divided by that. So it would take 360 seconds to fall a meter, right? And this is, there it is, right? So when you look up at a cloud, right? A cloud is really droplets of moisture. Those droplets are falling. They're just not falling very fast. So every cloud you see is falling through the air. Now the air itself might be actually rising faster than the droplets are falling. But to be sure, liquid water, which is what clouds are, okay, is more dense than air, and it is definitely moving down through that air. Okay, it's just that some of these terminal velocities are exceedingly small. Happy feeling.